There are various ways in which we can decrease the number of stall cycles in case of conditional branches or in any branch statement. So what happens is, we know that whenever we have let's say this is a 5-stage pipeline, 1 2 3 4 5 stages. Now whenever we cannot know what the next instruction address is, we are actually stalling. Let us say we will not know what the target address is until we finish the 3rd stage. Then we have to stall here and start the next instruction only at this stage, isn't it? So this entire time is wasted. So there are various ways that are currently being used by various processors in order to deal with this problem, right? So let's see the popular methods. So we are trying to avoid the stall cycles, but then we don't have any solution which will avoid every stall. We are trying to avoid it. In some cases we will be able to do it successfully, and in some cases we will not be able to do it successfully. Okay. So if you are lucky, our methods will work, and it is assumed that in 80% of the time they work. Okay. So now what the first one is, one method which is being, I cannot say the first one or the second one method which is being used is branch prediction and speculative execution. So this method says that whenever you have any branch instruction, see, sometimes what does the conditional branch do is, in case if the condition is true, if you are at instruction number 100, in case if the condition is true, from instruction number 100 you might have to go to instruction number 200. If the condition is false, then you will have to go to 101 only, isn't it? From 100 you might have to go to 101 in case if the condition is false. If the condition is true, which means if the branch is taken, you might have to go to 200. Therefore there are two ways: either the next instruction is going to be 101 or the next instruction is going to be 200, right? Then you are supposed to predict it, right? So this prediction is also sometimes called as guessing. So you are supposed to guess which one it will be, right? And then let us say we have guessed that branch will not taken. Under that assumption you will start fetching the instruction at 101, and after that 102, and after that 103, and you will be executing this sequence. And suddenly after the complete execution of 100, if you come to know that whatever we have started with, that assumption is wrong, that guess is wrong, then again we have to go with flushing, right? Therefore in this solution flushing is again involved, right? So if your guess is wrong, then maybe we'll have to flush it again. So sometimes we will be right with this, and sometimes we will be wrong with this. Whenever we are right, we are going to get a good performance. If you are wrong, of course there is no way we can avoid these stalls. So there are various ways, there are various methods by which this prediction has been implemented. So one way is to assume that branch is always taken, right? So some processors, whenever they come across this branching instruction, they will always assume that branch will always be taken, and so the next instruction will be fetched will always be 200. In case if they have any such instruction, the next instruction that will be fetched will always be 200. But after executing one on the address number 100, which is the conditional branch, if they find out that the branch is not taken, then we have to incur the penalty and we have to pay the fine there, right? So which means we have to flush the pipeline and again start from 101. And other way, some other computers, some other processors, they assume that branch is never taken. So in that case, what these processors will do is, even though the address is 100 now, okay, they will think that the branch is not going to be taken, which means they will always go with the consecutive instruction. This is the simplest way they can go with this, right? So they will start with 100 and after that they will get 100, then 101 and 102. See, branch is always taken. In this case they will start with 100, right, and then they will take 200, assuming that branch is always taken, and then they will take 201, right? In case if you can know the target address, 200. See, in most of the cases, after fetching the first instruction and during the decode phase, or sometimes they will combine the instruction fetch and decode in the same phase in such a way that target address will be known in the first phase itself, here itself, but then the condition will be known only during the execution time, right? Therefore, after fetching the address number 100, they will immediately start fetching address number 200, because branch address will be known in such systems, okay? And then 201, 202, they will fetch all this and they will continue this flow. And whenever, that depends on when we find out the exact condition when we execute it. So whenever the execution of instruction number 100 is over, then if you find out that our guess is wrong, then all these instructions have to be flushed and again start with 101, right? So now this particular strategy will perform better in certain programs where the branch will always be taken, right? Wherever there are more instructions in which branch is taken. In such, if all the programs are executed in that way, yes, this strategy will give the better performance, right? But then this strategy will fail as usual if the most of the instructions are not taking branch, okay? And the next way to predict is, assume that branch is never taken, which means after instruction number 100, we are going to start with address number 101, because our assumption here is that branch will never be taken, right? And then we continue with 101, 102, 103, so on. In case after executing this, if you find out that this is wrong and if the target address is 200, then we have to flush all this and we have to go with 200. So obviously this strategy will perform better if our program contains instructions in which branch will not be taken very often. Got it? It depends on what type of program it is. So there is nothing called this strategy is better or this strategy is better. It all depends on what type of instructions our program contains. Therefore, for certain programs, this might give you better performance, and for other programs, this might give you better performance. That depends on the nature of the program. And the other strategies are like, you can go dynamic methods. Dynamic prediction. So in case these two are nothing but static type of predictions, because once you design our processor will always assume that a branch is taken, or it will always assume that branch is never taken. Once you design the processor with this scheme, your processor will not be changed to this, right? So it is fixed. That is why they are called static. And other method is called dynamic methods. So in these dynamic methods, again we have two types of implementations. One is bit implementation, and the other one is buffer. There is a branch prediction buffer, right? So there is a name for this. Translation look aside buffer, like that. Yeah, I think branch prediction buffer is the name. So what does this bit implementation say is, for every branch type of instruction you assign a bit. Let us say the bit is B, okay? So bit B can be 0 or bit B can be 1, okay? So initially you can either start with the bit B equal to 0 or bit B equal to 1, which means whenever you come across any instruction, for every branch instruction we are going to assign, or we are going to reserve the bit B. In case if bit B equal to 0, and bit b equal to 1, we can assume something like this. So let us say, in case if bit b equal to 0, we assume that branch is not taken, right? In case if bit b equal to 1, we can assume that branch is taken. Okay, so now what we do is, let us assume that we are starting in this state. See, in which state do you want to start? That depends on the implementation. Either you can start here or you can start here, right? And if you are starting in this state, you are going to be in the same state as long as branch is really not taken, which means you have started out with the assumption that branch will never be taken, and as long as branch is not taken, you are going to be in the same state, which means, let us say there is an instruction 100. Whenever you come across it for the first time, you will assign the bits like this, and either you will start with the assumption that branch will not be taken or branch will be taken initially. And if your initial guess happens to be true, then you are going to be in the same state. Let us assume that you are coming across an instruction 100 and you are assuming that branch is not taken. Therefore, next instruction that you will get is 101, right? If this really happens that branch is not taken, and if 101 is the real next instruction to be executed, which means your guess is right. As long as your guess is right, you are going to be in the same state, right? So in case if your guess is wrong, which means you assumed that the branch will not be taken, but if the branch is taken, then you are going to change the state. Got it? And you are going to change the state and you are going to stay there. So what does it mean? You assume that the next instruction has to be 101, but after executing for some few instructions, you found out that the next instruction is 200. Then you will be changing it for the next time. So next time when you again come to the same branch instruction 100, which means for every branch instruction we are going to maintain a bit, right? And next time when you again come across the same branch instruction 100, then we'll check this one, right? Now we'll check this and we'll see what has to be done. Last time we stopped in this state, right? Which means we are now assuming that branch will be taken. So the next instruction will be fetched will be 200 only. Okay, so as long as branch is taken, which means if you guess that the next instruction is 200, and if it really happened that the next instruction is 200, then as long as branch is taken, you are going to be in the same stage. In case if you are assuming that the branch will be taken, but it so happened that after executing the instruction you found out that branch is not taken, then you are supposed to change your state, right? So branch is taken and branch is not taken. So depending on that you can have it. So some implementations they even use two bits. So they say that 0 0, which means branch is not taken but it is a weak state, and then 0 1, it also says that branch is not taken but it is, let's say this is strong and this is weak, strong and this is weak. Okay, and then again 1 0 and then again 1 1. So this will be weak, branch is taken, and this will be strong, branch is taken. So instead of using one bit, some implementations will use 2 bits. So what is the advantage of 2 bits is we will give it a second chance. So which means if you start out with the assumption that branch will not be taken, when the branch is taken for the first time, instead of directly going into the mode of taken, we'll still stay in the mode of not taken and we'll give it one more chance, assuming that okay, let me give it one more chance. It might be last time might be the last wrong guess. So whenever you guess wrong, which means here you are assuming that branch is not taken, as long as branch is not taken you are going to be in the same state. If the branch is taken, which means if you are wrong one time, then instead of directly changing your opinion, you will just stay in a next state and wait for one more case, right? In the next time also, when you are here, and when you are assuming that branch will not be taken, if the branch is taken, then you are going to change your opinion. Got it? So here we are just changing your opinion based on one wrong guess. But here, if you have to change your opinion, you have to actually go through two wrong guesses. Got it? And in case if you are in this weak state, which means you don't know whether to go to branch taken state or not taken state, and here if you get something right, you are assuming that branch will not be taken. If the branch is not really taken, then again you will become strong and you will assume that branch will not be taken. Got it? And now when you are here, when you are in the weak state, you are assuming that branch will be taken. As long as branch will be taken, if the next branch will be taken, you will become stronger, right? And if the branch is not taken, again you will come back. Got it? And here you are strongly believing that branch will be taken, and as long as branch will be taken, you will be strong. If the branch is not taken, then you will become weak and you will come there and wait for one more wrong guess to go back to this. Got it? So there are various implementations. So this is one type of implementation, that is other type of implementation. And the other type of implementation is maintaining a buffer, branch prediction buffer. So what happens is, in this case we'll have a look aside buffer. Okay, that is a high speed cache. So in this buffer we are going to maintain the database like this. So what is the address, branch instruction address, and what is the target address? So whenever you come across any branch instruction for the first time, we'll note that instruction address and we'll note the target address, what has happened this time, and next time when we come across the same branch instruction, we'll try to take this one and execute it. So here we are assuming that last time whatever has happened will again happen, right? So that kind of implementations are also there. So what happens is, whenever you fetch an instruction, see how do you fetch the instruction? We'll send the program counter to memory, right? So along with this sending the program counter to the memory, along with this we'll also send it to the TLB, translation look aside buffer, and this particular TLB is dedicated only for branch prediction. And whenever there is a hit in the TLB, it means that the current instruction that you are trying to fetch is a branch instruction and it has already been seen previously earlier, and we know what the target address is. In that case we'll get the branch instruction and we'll take this one for the next fetching. Got it? And in case if it so happens that if you started with the next instruction as 200, because last time it happened to be 200, and if this time it is wrong, then again you have to update it to 101. Once you finish the execution of address 100, you have to again update if you are wrong. Okay, so these are all the various ways we can deal with this problem, but there is no 100% guarantee that you'll always be able to avoid all these stalls. We'll not be able to avoid all these stalls completely, but to some extent these can be avoided. So whatever we discussed here is called as branch prediction and speculative execution. And there is one more solution. This is solution 1 or way 1. So first way is by using branch prediction and speculative execution, and the second way is called as delayed branching. We'll see it now. Okay.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177, and IIT Roorkey's ranking is 400. If you are happy to get into IIT Roorkey, then getting into universities better than IIT Roorkey is easier compared to getting into IIT Roorkey. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.